All right, so this is the exponential growth and decay functions. I really like this section because it talks about way things like either appreciate or depreciate in value over time exponentially. So this is the exponential growth equation, y equals a, and then I put 1 plus r to the t power. The other equations you would use would be y equals a times b to the x power. T and x are basically the same thing, which would represent our amount of time. So by month, by year, annually, every year, that would be the number that goes in for that exponent. B, I'm kind of working backwards here. B is what is known as our growth factor. All right, and our growth factor will be represented by 1 plus r. And r would be our growth rate, which would be typically a percentage. All right, and so within these problems, we're going to have to convert a percentage to a decimal, and then either do 1 plus that percentage as a decimal or 1 minus the percentage as a decimal when we get into decay. So that's the only difference between the two. And A is the initial amount of what we're working with. So we're going to identify the initial amount. We're going to identify the growth factor represented by B by doing 1 plus the percentage as a decimal. And then our variable will be time. You typically, again, like every year, 2 years, 3 years, but we'll set up the formula so that we can then put a different amount of time in so that we can get our output. All right, so this is the setup, and this is how we would do a problem like this, and we're going to practice this later as well. So the first question says you deposit $500 in an account that pays 8% interest compounded yearly. So this would be every year. And compounded means it's making 8%, not on the 500, and then when you do the 8%, you'll have a new amount. So the next year, you're making 8% on whatever that previous year's amount was, not just the initial 500. So that's what compounded means. So instead of 8% on 500, you're making the second year, you're making 8% on whatever the 500 made on that 8%, and so on and so forth. So what would the account balance be after 6 years? So how will we set that up? So we first have to identify the initial amount, which is our A. So in this case, A equals, and our initial amount is $500. Then we have to identify the rate as a decimal. So our rate would be 8%. So we talked about the other day, 8%, the decimal's here, we move it over 2 spaces. So our 8% as a decimal is 0.08. Now, to figure out our growth factor, we need to do 1 plus that, right? So we have our rate as a decimal, so we are going to do 1 plus this amount, 1 plus 0.08, which would give us 1.08, and that's what we're going to use as our growth factor. So this is essentially our B right here that we're going to use in the equation. So now we can set up that equation. We can say y equals 500 times, and then here, right here is our growth factor, 1.08 to our x or t power, right? And you can interchangeably put x and t. So then we identify the amount of years. So we have years in here. So we are going to set up this equation now and put 6 in for x. So we have y equals 500 times 1.08 to the 6th power. And we like to set it up with the x first because I could say, hey, after 2 years, after 3 years, after 20 years, you can do that. So now we're going to take out our calculator. Okay, so now I can type this in here. So 500 times 1.08, and then I'm going to put the 6th power in here. And it's dealing with money, so our final answer would be 793, and I'm going to round to the nearest cent, so 0.44. So after 6 years, 8% interest, you go from 500 to almost $800, so almost $300 just on something that is collecting interest. And that's how compound interest works. All right, so for this example, suppose your community has 4,512 students this year. the student population is growing, and growing is telling us that it's going to be an increase. So that's where that 1 plus comes in. Write an equation to model the student population to calculate what the student population will be in 3 years. So A is our initial amount. So we have our A equals 4, 5, 1, 2. Our B is going to be 1 plus 2.5% as a decimal. So 1 plus, and 2.5%, again, I move that 2 spaces, and I put a 0 there. So it's 1 plus 0.025, and that would equal 1.025. So that's a 2.5% increase. So once I have my A and my B, I can write the equation. Y equals 4,512 times 1.025 to the x power. All right, and then in this case, we're going for 3 years, so then I can put the 3 in for x, and I type that into the calculator. So let's go ahead and do that. So this is what I'm going to be typing in. I don't have to type in the y equals, but 4,512 1.025 to the third power. Let's go ahead and find our answer there. Times 1.025 to the third power. Put that there, and that gives us 4,858. And again, I guess we're dealing with human beings and people, so we'll round that to the nearest whole number based on the context of the question. So the answer would be 4,858, or I will go 59 as our answer there. All right, so the next portion we're going to deal with is a decay. All right, so the difference between growth and decay is either 1 plus or 1 minus, right, is going to be the growth factor. So before we get into a decay, it's pretty easy to see whether a function is a growth or a decay because we can look at the actual growth factor, the number that's being raised to a power. So if that number, because when we think we're going to be taking 1 minus a decimal, right, so it's going to be less than 1 would mean a decay, and anything greater than 1 would be a growth. So if we look at these following situations, and we can label them either G for growth or D for decay, we just look at what's in parentheses. If that number is greater than 1, it's a growth. If it's less than 1, it's a decay. So if we look at this, this is less than 1. That's a decay. Greater than 1, growth. Decay. And I'm just looking at it does not matter. The initial amount does not matter. It's just the part, your B, that's in parentheses. This would be a growth. This would be a growth, decay, and again, a decay. All right. So when we set up how to do a decay, the only difference is we have to take 1 minus that percentage, that percent written as a decimal. All right, and that's where we will get it less than 1. So let's go ahead and look at this sample problem. So suppose you buy a new car valued at $40,000, and the car depreciates in value each year by 7%. What is the value of the car after 4 years? Well, we set up the problem exactly the same way. So we have our initial amount, which is $40,000, and our growth rate would be, it's really a decay, but we're going to call it growth, would be 1 minus 7% as a decimal. So again, 7%, we move the decimal place over twice, put it there, fill it with a 0, so it's 0.07. All right, so our growth rate, when we type that into our calculator, and we type in 1 minus 0.07, that gives us 0.93. So our growth rate, or our B, is going to be 0.93. That's what we're going to put into our equation. So here's our A, here's our B. Our equation is Y equals 40,000 times 0.93 to the X or T power, whatever you're going to use. All right, T in this problem would be 4, because that's our time. So after 4 years. So then we put that in for our x and we solve. So 40,000 times 0.93 to the 4th power. And we'll just go back to our trusty calculator and figure it out. 40 times 0.93. And in this case, we're using after 4 years to the 4th power. So that gives us, again, we're depreciating, so this makes sense that it's less than 40, right? So we have 29,922. We'll round to the nearest cent, which would be 0.08. All right, so that's the lesson on growth and decay. A lot of it is just setting it up. It's pretty straightforward. This is our light introduction to this material.